Welcome to section 14.5, surface area. In this section, we are going to learn how to find areas of surfaces in space. So, as a reminder, the length of an arc that you studied in AP Calculus BC could be found using this formula here. And we're going to look at an element of proof of how this formula comes to be. If you have a function of one variable, so you have a curve in the plane, and you're trying to find the length of this curve from a certain point A to a certain point B, then you want to add all these tiny segments, delta S, and you want to add them as they get smaller and smaller, as the length of delta S approaches 0. So how long is delta S? It's approximately, you can find it approximately using the Pythagorean theorem. It's the square root of delta x squared plus delta y squared. And from this point here, you can rewrite the second term, delta y squared, as you can multiply the second term by delta x squared over delta x squared. And that allows you to factorize delta x squared inside the parentheses. So you have delta x squared times 1 plus delta y squared over delta x squared. And then the delta x squared that you factored out, you can pull it out of the square root, and it's delta x. So delta y squared over delta x squared can be written when we actually go to infinitely small intervals as dy dx squared. So here's how you get the formula that we just mentioned. The formula to find areas in space when you have a surface is very, very similar, as you can see. It's a double integral, but then it's 1 plus the first partial derivative squared, and then plus the second partial derivative squared, dx dy. So we can see how this is similar, how it kind of naturally expands from 2D to 3D. So we're also going to talk about an element of proofs here. So if you have a surface in space, you're going to want to break it out into small little pieces like that can be approximated with parallelograms. So the red parallelogram is going to have approximately the same area as this little piece of surface in black. And then again, through the limits process, as we narrow down our grid and the red parallelograms become infinitely small in both directions, so both edges are infinitely small, then we get an exact value for the area of the surface. So to do that, to find the area of a parallelogram, we actually have the tool. We know that it's the magnitude of the cross product of u, if u stops here, and v. So what's important here is to choose u and v so that they are well oriented. So u is going to be a vector that is in the xz plane. So I kind of showed what it looks like for this sketch. So u has no y component. And then v is in the yz plane, so v does not have any x component. The reason why v here is not exactly parallel to the y-axis, and the reason why u is not exactly parallel to the x-axis, is that they may still go up or down, right? If you go a certain amount of steps in the y direction, it might go up in the z direction because u and v are tangent to the surface at the point here. So how can we write these two vectors? Well, u is delta x. It's the same as we did in 2 dimensions. It goes in the x direction by delta x steps, and then 0 in the y direction. And then how much is it going up or down? Well, that's exactly what the first partial derivative tells us. It goes up by the slope in that direction multiplied by how far we went in that direction. And we went delta x in the x direction, as can be seen here. So the vector u is delta x 0 fx delta x. Likewise, vector v goes in the x direction by 0. It moves in the y direction by a certain amount delta y, and then it goes up or down by the slope times delta y. So now that we have set up what u and v are, we can look at the magnitude of the cross product, because this is the area of the parallelogram. And so for cross product, it's the first step is going to be 0 times fy, so that's going to be 0, minus fx times delta x times delta y. And then for the second component, so it's minus delta x fy plus fx times 0, so we get this second component of the vector. And then eventually for the last component of that perpendicular vector, it's delta x times delta y minus 0. So we have our perpendicular vector. What is its magnitude? We use the Pythagorean theorem for that, and we get exactly what we could have expected right here. So you may notice that we pulled out delta x delta y since it appears in all terms. So that's an explanation, or at least an element of explanation, of where this formula comes from. We are going to see one example of this applied. So find the surface area of the paraboloid z equals 1 plus x squared plus y squared that lies above the unit circle. So above the unit circle we have this shape. It looks like a contact lens maybe. So it is cut here on this circle. What is the surface area of that? So we're just going to apply the formula. It's the integral on the given region of 1 plus the first partial derivative squared. So what's the first partial derivative in terms of x? It's 2x. That's why it's 2x squared, plus fy squared, which is the first partial derivative in terms of y. It's 2y squared dx dy. That's 1 plus 4x squared plus 4y squared. So we can, and it seems pretty clear since the region is a circle, that we should switch to polar coordinates. So it's 1 plus 4r squared times r dr d theta. Theta goes from 0 all the way to 2 pi, and r goes from 0 to 1. So from here on, we can use u sub, for example, or maybe we can guess what the integral is going to be. But if you use u sub, you just put u equals 1 plus 4r squared. Therefore, du is 8r dr. And we can substitute all of this here. Notice how this changes it changes the boundaries of integration. When r was equal to 0 here, that means u is equal to 1. And when r was equal to 1, u is equal to 5. So remember to change that. If you don't want to change it, then it's better to write nothing as the boundaries of integration, and then later when you substitute back to r, then you can safely put 0 and 1 again. So we integrate, we substitute r back, and this is where instead of integrating from 1 to 5, we can integrate from 0 to 1, which is fine. You could have substituted u equals 5 and u equals 1 right there, or maybe it's an extra step, but it's a little bit more safe. Go back to r and substitute 1 and 0, and in the end, you get this area. This surface is actually a surface of revolution. We are revolving about the z-axis. So with what you've learned in AP Calculus BC last year, you actually had the tools to find this same value as well. You can try if you want, but of course the formula we see now is much more flexible, and it has a lot more potential because it does not require the surface to be a surface of revolution. Thanks.